Thanks again, everyone, for joining us. For those of you who have just joined, my name is John Sosa, CEO of MIPAR Software, and joining us today is Paul Sewell, Senior Application Specialist at MIPAR Software. So, to begin, MIPAR, as many of you may know, is a very versatile and efficient platform for image analysis of all sorts of applications. It is a visual algorithm builder, essentially, for image segmentation and analysis. These visual algorithms we call recipes. They're very easily created in the software. They're available up on our recipe store. We have over 50 made recipes available on our store, which I'm showing to you now in our web browser. They're organized by different sections, and you can browse through any of these and download any of the pre-made recipes that are available. Store is fully searchable, and we grow this quite aggressively. So with over 50 available now, we expect to double this in the very near future. We also have the ability for you to submit to us images for our team to create custom recipes for you, and this is an incredibly valuable opportunity. You get up to 3 custom recipes for free during the trial period, and then there are, of course, options for additional custom recipes beyond that. So you'll see recipes made and loaded today quite frequently during the webinar, and it really is the core technology of MIPAR. The flexibility and efficiency with they are made really allow MIPAR to tackle all sorts of image analysis problems. So with that, we do have a couple of distinguished guests with us today. They are early adopter users of MIPAR that were with us from the very beginning, and they very generously agreed to share some of their experience with you and how MIPAR has helped their research and other activities. So if he's available, I was going to invite Brian Martin from Iowa State University to share some of his experience with you, and we'll go ahead and give him that opportunity. Brian, are you with us? Let's give Brian a moment here. Okay, perfect. Thank you, Alden. No worries. Well, then, while Brian is calling in, we also have Philippos from MIT joining us, who is also willing to share some of his experience with MIPAR. So, Philippos, can you hear us?
Yes. Hi, John. Hi, Paul. Can you hear me?
Yes, we can hear you loud and clear. Thank you so much for joining us and being willing to share.
No, you're welcome. Thanks for the opportunity. So, hi, everyone. My name is Philippos, and I'm a postdoc associate at MIT, and specifically at the Center for Bits and Atoms. And the research we are doing here is we're exploring the boundaries between digital information and the physical world. So when we do that across different scales, and it's very interdisciplinary. So my physical world are cell shapes, and specifically biological cell shapes, stem cell shapes. And I'm using in my research manufacturing technologies where I can manipulate the cell shape and then guide cell function. And 2 years ago, so most of my time I'm a mechanical engineer by training, and I spent most of my time building machines. And towards the end of my PhD, when everything was working and I had a lot of data with specifically confocal microscopy data, 3 different channels, 3 different colors of stem cells, I had to do some analysis because the basic topic of my PhD was metrology of cell shape. So I had to find ways to model cell shape and quantify specific features. And some of these features were really, very hard to detect. There were proteins that were numerous, they had a big number of proteins in each single cell shape and very small in size. So you can imagine without any training on image processing and computer vision, although there were some open source softwares, when I came across MIPAR and I started using it as a beta user, I literally saved 1 year of my PhD. 1 year of coding, combining different image processing algorithms for objective segmentation, and of course classifying certain features. So yeah, I'm really excited that I have this tool, and I'm using it for not only not only for biological studies, but also characterizing different types of materials that I image under SEM. So yeah, and basically I'm using MIPAR, and I can very fast process a huge amount of data, and MIPAR basically plays the role of feature extraction, because we are using machine learning, and you need to extract very meaningful features, and this is the most important step for your machine learning tasks, especially when you do classification. So MIPAR has been very instrumental in my research, and I have been publishing. I have 2 conference papers due to MIPAR, 1 journal paper before Christmas, and another journal paper that we are using MIPAR again, and we are showing our metrology, platform for cell shapes. And yeah, that's what I'm really.
Thank you so much, Philippos. Thank you very much. I greatly appreciate you joining us. Your feedback means more than you know. It's been a pleasure to have you on board as our user and customer, and we're delighted to hear the impact that our team and MIPAR has been able to have. So we are very excited to continue to have you on board.
Thank you.
So thank you so much for joining us and being willing to share.
Yeah.
And we'll stay in touch.
Thank
you very much.
Bye-bye.
Hope you enjoy the webinar. Thank you, Philippos.
You're
So thanks again to Philippos for being willing to share his experience. We're very humbled to receive comments and notes like his on a regular basis. And it's putting a user-friendly, user-oriented tool in the hands of as many people as possible is really what we're about. So it means a lot to have feedback like his. In the interest of staying on schedule, we are going to move on here to some of the rest of the agenda and start in with the material science section. Brian, thank you very much for joining us. We'll do our best to work in your feedback that you're willing to share during the rest of the webinar, and I'm sure we'll have that opportunity. So to begin, I wanted to start with a very simple second phase example. We call them simple particles, and we'll open them up here in MIPAR and get started. What you see in front of you is the image processor. This is the most commonly used application in MIPAR. It's where recipes are built, it's where they're executed on single images, and it's where a suite of other analysis is conducted. So to open an image, you can simply either click Open Image and choose the file, or as we like to do, drag in the image here. That opens it up. So what we have here is a two-phase microstructure. For those of you familiar with that term, we've got particles, we've got a matrix. We have a recipe available to detect these particles separate from the matrix. This is one of the recipes available on our store under the material science section. To load it in, it's the same as opening an image. Either click Load Recipe and choose the file, or simply drag in the recipe. This is going to execute that recipe, and you now see the particles and matrix detected separately. You've got the matrix here in blue. I'm just going to show and hide this layer. And you've got the particles in red. So what this recipe is, as I've mentioned, is a visual algorithm. It is a string of image processing steps that piece together to detect your features of interest. It's completely non-destructive, so you can edit any of these steps at any point along the way. Double-clicking on them shows you the result of that step, and you can get a feel for the logic involved in constructing this recipe. So like I mentioned, editing a particular step, adjusting any of its settings, and accepting it will cause the recipe to automatically rebuild, which can't even tell you the number of hours that that saves when constructing these algorithms. Steps can be removed at any point. New steps can be inserted. When you click a step from up in the menu bar, whatever step you have selected is put underneath. So let's step through here and actually rebuild this algorithm from scratch so you can see that process. So let's clear this out. What we did is we started with a smart cluster step here under segmentation, which you decide how many classes you want to break up this image into. We used 3 for light, medium, and dark. This is a pretty objective way at going after these problems since you're not selecting a threshold level. So we've now broken this up into 3 classes. We've got 3 grayscale values in here. That step's been auto-recorded. And now we can go and grab a threshold step where we will simply select, you've got, it's hard to see, but you've got in your histogram, you've got 1 class down here, a middle class, and the brightest one. So we're going to choose bright here and select the mid-level and brightest class, and now we've selected the particles. We're then going to add a couple of cleanup steps that are usually good practice. You can find those under the Morphology tab. Under Dilate and Erode, we've got Smart Erode and Smart Dilate, which will get rid of some of this sparse noise in both the matrix and the particles. So let's do a Smart Erode first. Hover over these steps to get an idea of what I'm already setting to see what they do. You get some recommended values for some of them. So we'll use a 5 here. And then we'll use the same setting for a smart dilation. We'll use a 5 here. And this is filling in some of this sparse noise you can see. So you'll notice that any step that is a selection step that's resulted in something being selected in the image has different viewing modes. You can look at this as a black and white image, where black is a binary image, where black is what is selected. You can view an overlay of your selection of the current reference. You always have these linked side-by-side viewers. You can take any image over here, right-click on it, and set it as the reference if you wish. You've got Outline View, which shows your current selection outlined on the reference. And oftentimes what is most helpful is Labels View, where you've got random coloring assigned to each separate object. So here we see, even after the cleaning, we've got several particles that are inaccurately clustered together. We know from our expertise that these should be identified as separate particles. So we'll want to go ahead and add a separate feature step here. We drag this up, and we start drawing lines separating the objects. So many of these look properly separated now. You'll notice over here we've got a couple of inaccurate separations. We don't want a line drawn through this particle. So we'll just decrease the separation strength a little bit more until we still have separated what we desire with no artificial or inaccurate particle cuts. So let's accept that, and now you can see under Labels View, you've got particles accurately identified. The last step that I would throw on here is a Reject Features, which in this case can be thought of as setting the minimum particle size. So let's, under Cleanup, you'll notice we kind of move left to right in constructing this recipe. You've got all of your filtering, intensity, manipulation, texture enhancement, noise reduction tools, initial feature selection, more feature selection, selection manipulation, separating smoothing, dilating, eroding, artifact removal, and memory setting, which you'll see used quite a bit today. So under here, under reject features, what we're going to do is just go in and look at something very small. I'm going to say that, you know, this might be the smallest particle that I want to be identified as such. You can reject features on the basis of any of these shape and size parameters. All of these preview GUIs also have a help button. Click that and you're taken directly to that particular page in our online user manual with all of these explained in detail. There are references down here for many of the functions that are tied to papers. And this is consistently updated for you. And again, with it being online, we're able to do that quite efficiently. You can also take the manual and export it as a PDF for yourself if you'd like. So I'm going to say I want to set my minimum size on the basis of area. So go ahead and click your measurement tool and click on something that interests you. You see now you get the area of that printed out. That's 15 particles, or 15 pixels. You know, you can switch to any of these and you'll get that selection updated. And you can see additional metrics that you may want to use for your feature rejection. I'm going to say 10 pixels will now be my minimum particle size, so reject anything under that. If I had chose 20, then of course you would see that particle go away. But we'll keep 10 as the threshold here and accept. So now we have our recipe. We can polish this up a little bit and set chapters. We can say that these initial 2 steps here were for the initial particle selection. These 2 steps here were for some noise cleaning. And then this chapter here was for separation. So it just helps group steps together and give you a plain English overview of exactly what the algorithm is doing. You can flag certain steps as critical to the selection. So say if some parameter of smart cluster was very important, go ahead and flag that. That tells you and other users that if the recipe doesn't work, the flag steps are probably the first ones that you should look at adjusting. The separation strength is important, so I'm going to flag that. And you can also add custom notes to any step to explain to yourself or to others what that step is really doing for you. You, of course, always have the default help text there, but you can always add notes like targets, particle, separation. And this one here, you can say flag sets minimum particle size. And now you can save that recipe away. Imagine that you had another image to run this on. You drag it in, and you can just say open that image and reload. It will open that image for you and reapply your algorithm and select your features. So that's the first recipe we wanted to start with, a pretty basic one, but even though MIPAR is very good at the problems that others have trouble with, it of course excels at the simple ones and allows you to tackle the simpler problems more efficiently as well. Simple porosity finding or other particle detection and measurements are also made very efficient given MIPAR's interface. So what we'll now do is move on to a different application, cracks and pores, which is one that we see quite often from folks. And once I show this particular recipe, then we'll go back and look at quantification for both of these applications. So let's start with a crack and pore example. Clear this out. We have here, I'm not entirely certain what the material is, but you see we have these rounder pores and these thinner cracks. So here's a recipe we've put together for applications like this. And we end up now with the cracks detected as one type and the pores as another. I'm not going to rebuild this entire recipe in front of you for the sake of expediency and simplicity, but I will step through the different chapters to highlight what the overall structure of it is. You notice we have a background gradient, other challenging artifacts. That's all been taken care of here. So the first step here goes and performs a noise reduction. Then we use another smart cluster. In this case, we divide it again into 3 classes, and this helps this particular recipe work nicely on other images. Rather than a simple auto threshold where you're only deciding on one delineation intensity value, what is bright and what is dark, this smart cluster is dividing it into 3 types, saying what is very dark, what is in the middle, and what is very bright. And that helps the robustness of this recipe, and it helps it work across other cases like this. So now we have our smart cluster. We select the darkest class, which are our pores and cracks. Let me show that as an overlay. We put this into a memory slot. We've got 6 of them, and the companion image, which is the most important memory slot. We can recall any of these memory slots later on. So let's go forward and see what we've done. We've ignored any particles that are very elongated. So you notice we've rejected, on the basis of eccentricity, anything that's very elongated, to start to capture what we call our obvious pores. Then we get rid of pores that are very rough. So this object here is considered very rough. What roughness is really doing very quickly is we are taking, let me hide this step and just show you, if I replace everything with its convex hull, then what you're going to see now is, and I'll show this here as the reference. So a roughness of a feature is measured as what's the tightest fitting convex hull around it, what's the area of that hull, divided by the area of the actual feature. So the minimum roughness is 1. That's a perfectly smooth object where the hull matches the object. And then the more rough the object gets, the more abstract arms it has and whatnot, the greater that number is going to be. So let me remove that step out now and turn on the remainder of the steps. I'll let them rebuild. And now we see we've removed particles that are very rough, that have some protrusions off of them. So here now what we're calling our obvious pores. We then set this in memory as the companion image, which lets us add it to other images later on. We also set it in another memory slot. And then we are going to recall our initial selection of everything that could be a pore or a crack. And we go and subtract now our obvious pores, which are stored here, from this image, giving us this image. Now we're going to say here is everything that could be either a crack or a pore with a crack connected to it. So we are going to erode everything to break apart all of the connected cracks and eliminate all of the very thin ones so that we're just left with what could be remaining pores. We reject very small pieces like these here. We say anything that's under 20 pixels we don't want to regrow to consider it a pore. So now we regrow everything, and when you see by going through these 2 steps, we've gone from this to this, and we are just left now with the rest of the pores that weren't so obvious. So we add the 2. We add what we've grabbed here to our obvious pores, which are up here. So from a math feature union step, what that will do is it will combine the current selection with whatever selection you have in the latest companion image. So you move up in the recipe, find the first companion image. That's what the feature union will add to your current image. So we combine the two like that. Now we do one final minimum pore size setting. This is actually done in units of microns. We've calibrated the scale of this image, so we know what the physical size of each pixel is in microns, and we can now reject any pore that is under 2 microns in diameter. That's just what we've set for this recipe. For example, edit this, and you can see we've selected equivalent diameter as the unit, or as the measurement, units of microns. You now get the equivalent diameter. Let's move this on over in units of microns here. So if we were to put 3 as the threshold, then these small ones would get ignored, or even 4. Point being that you can set your size threshold in physical units rather than just pixels, which can be extremely helpful at times. So now we have the pores selected. We've gone in and now we slightly grow all of the pores to make sure that they fully subtract from our initial everything selection. So we take the slightly dilated pores, we set them as the companion, we call our everything selection here memory 1, and we subtract the 2. And now this gives us the cracks. Now you notice there's a new viewing mode that we're seeing called layers. Layers are steps that you set as very important. You give them a name and the color. That lets you co-overlay them together, and it also lets you do some handy things with measurements, as you'll see. So imagine that we hadn't set these as layers. Let me unset these as layers. Your available options are these standard 4. We know at this point in the recipe is where we have our pores selected. So I'm just going to click on that step, say set layer. Now I can name it as pores and give it a color. It's then going to kick you into layers mode where you're just looking at all of the layer steps. And then we go down here where we have the crack selected at step 19. We set this as a layer, give it a color, and now we've got just the important steps color-coded to their names and only shown from the recipe. And as you saw before, you can show hide these layers. So layers plus the linear, yet at times nonlinear workflow of the recipe, given the memory step capabilities, really allows you to tackle an incredibly wide range of image analysis problems. So that's a pore crack example. What I'll now do is launch right into quantification, starting with this example. So we have our layers identified as pores and cracks. When you're in layers mode and you choose any of these global measurements that are available, they are conducted on all layers at the same time. That's one advantage of setting layers. So if I wanted to measure the volume fraction of the pores and the cracks, simply be in layers mode and click area fraction. You get this prompt here. You'll almost always use entire image. We recently added this feature. What this lets you do is if you have a non-rectangular area of interest that you're looking at measuring area fraction relative to, say you have a circular disk in your sample and everything else is black outside of it, and you select something inside the disk and you want to measure that selection, not relative to the whole image, which has a bunch of black space, but relative just to the disk, then you have your disk selected and stored in one of these memory images. And then you can measure the area fraction of your selection relative to the area of that disk, as long as that disk is selected in a memory image. So that's just the purpose of this drop-down. Again, most area fractions will just get measured relative to the whole image. So you'll just click Accept, and now you get a table color-coded to the layers that give you the area fraction of both selections. What's very nice is when measurements are added to the recipe. So let me just save a version of this here, call it with measurements. If you were to have a new image, let's say, you drag in a new image, you say reload. Not only will the feature detection be done automatically for you, but then right at the end, up pops the measurement table color-coded again to the layers. So with one drag, you've now both detected your features and measured them. So we, of course, have other measurements available. You can count the number of features in each layer. You can count, say, you can measure the total area of both features. You could look at the number density, number of features per square micron. And now you've got a number of measurements that are added. Global measurements are all of these. These are ones that result in one metric per layer. What would happen if you loaded the recipe now is the same as what would happen if you clicked on this Generate Report button. This will then perform all of the measurements that you have down here all at once and put them in one nice table, again, color-coded to your particular layers. So you see, you get all your measurements reported for both layers at once. So those are global measurements. I'm now going to cover feature measurements by looking at our original example. So let's clear this out, and let's go back to our particle case and take our recipe. Let's say we wanted to measure the shape and size of each particle. Well, first of all, what I'm going to do is insert, before I name my particles layer, let's add a kill edge features step. So right after I separate under step 5, I'm going to say clean up, remove edge features. Now I've ignored everything that touches the edge, so I only have fully contained particles. Now if I'm going to measure their size, let's say, I'm not going to want to do that in pixels. We need to calibrate this image. You can see there's no scale factor set. The image hasn't been calibrated. There's no scale bar on this particular image, but we do have one that does have a scale bar. It's good practice to always have scale bar images taken at all the mags that you work at. In MIPAR, you can calculate your scale factors from each of those scale bar images, and you can then save that scale factor as a cal file, say 20x.cal, 50x.cal, 100x.cal, and you can then have just a library of those cal files that you can share internally, and you'll never have to calibrate magnification again. But once you have that library, then there's no need to put scale bars on all your images, provided you take images at, you know, a similar set of mags and image resolutions. So what I'm going to show now is setting the scale bar for one particular, or for setting the scale factor for this case. So we'll say calibrate. We're going to load a different image since this one doesn't have a scale bar. Let me pick the one that does. And I'm going to zoom down in here, roughly where my scale bar is. We recently added our auto detection feature, since what's been troubling in the past in just about any software that's out there is the imprecision that comes with setting the scale. You know, the microscope printed this scale bar on here, pixel for pixel, knowing exactly what the scale factor was. So why then should we go in and have to guess at where to draw the line? You know, you can take this line tool and you can drag it across, and you could stop there at 204 pixels or 206. There's just no need for this imprecision to be introduced into the analysis, since again this number was known absolutely when the bar was printed on. So we've come up with an auto detection mode that will replace or take away, eliminate that unnecessary uncertainty. So you zoom in to roughly where your scale bar is, you click auto, the blue box just tells it where to look, and when you click plus or check, it will search for the scale bar, and 9 times out of 10 draw a line right across there. If it fails, you're always welcome to adjust the search area, and just about any time that the initial search fails, adjusting your search area will correct the mistake. So it searches, it finds the bar, pixel for pixel, it puts a line right across it, And now you can just say 50 microns is that distance, calculate, now you have your scale factor. We support all kinds of bars. As you notice, this split bar works. Certainly long connected bars work just fine. Even hash bars that are seen on Hitachi SEMs, where you've got 10 different hashes that span a total distance, our algorithm works with those as well. So we're very excited about the reduction in that unnecessary uncertainty that this provides. So click Accept now, and you've added your scale factor to the box. Again, you can save this as a number, save it as a cal file. And now, with the image calibrated, we can make measurements in units of microns instead of pixels. Simple measurements, measuring one object, can be done using this interactive tool. Click a measurement, or click a feature to get their measurements. You get a scrollable table with all of these metrics for that object. But what we often like to do is measure everything at once. So if you simply want a spreadsheet of everything, use Measure Features. You can extract these size, shape, location, and other measurements for every feature in one spreadsheet. Spreadsheets don't always tell the entire story, and sometimes if you're limited to a spreadsheet of data, you can miss spatial trends or histogram shapes, typically spatial trends, so the location of different measurements of different features can easily be missed when only looking at spreadsheets. So our color by measure tool is extremely valuable in a lot of cases. Go into color by measure, and you can generate those same measurements. If you already had the spreadsheet made, you can load that in right here, but you can also generate them initially from this tool. So let's check off ferrets diameter. That's the longest length that fits inside of an object. Let's check off eccentricity, which is a normalized aspect ratio. So a straight line has an eccentricity of 1. A perfect circle has a value of 0. Roughness, we've already explained, can be a measurement of how smooth something is. So we'll hit Generate. We'll make those measurements for every object. We now have a table. We've got 236 particles in this view. We've got each of their measurements here: roughness, eccentricity, ferrets diameter. Simply click on any cell in the column of interest. Let's say we want to color code these according to size. Just click a cell in the size column. Now you've got the particles color-coded according to their ferrets diameter, with a corresponding color-coded histogram here as well. Whatever cell you have selected here, that feature is highlighted in the image, so you can see exactly what is this feature 23 that has a diameter of 33 microns. It's that one. And then we're bidirectional, so click on a feature on the image, have that cell highlighted in the table. That one is feature 174, and it's got a diameter of 58. This one down here is a little smaller, diameter of 40. And you can easily switch between measurement types. So click on eccentricity. Now you have particles colored according to how round they are. Blue is round, yellow is very elongated. Here they are colored according to roughness. This can be a very valuable tool in helping you decide, are there important parameters at play that can be meaningful to your microstructure characterization. You can also take this table, you can export it into Excel. Maybe you have some custom algorithm that can perform some linear combination between these measurements and come up with some sort of fourth column that you use internally, some sort of fourth measurement that is a combination of these three. You can then load that adjusted spreadsheet back in and then color code everything according to your custom measurements. And often we've done this where we've taken cancerous and healthy cells. We've come up with some algorithm to predict whether they're cancerous or healthy based on their measurements. You can take that, cancerous or healthy prediction. I know I've jumped out of bio, but it's the first thing that came to mind. Put that prediction back into your table and color code your objects according to your prediction, and that can be a real nice visual interpretation of how accurate your predictions are. So a lot of power in this tool. You can turn on Show on Histogram, and you see now whatever thing you have selected a line where it sits on the histogram is also shown. Adjust your bin size, change your font size, choose to just use single coloring instead of color coding it to the same map. Save this picture, export this underlying data to Excel, export this data to Excel. It's very friendly to take data out of MIPAR and use it in whatever reporting software you are looking at. So that is feature measurements. I didn't plan to, but I quickly would love to jump into just one example of local measurements that you can do. Let's actually go back to a case where we've got all the particles selected. Say local measure. Let's say you wanted to visualize how the local volume fraction of the particles change. Just use your area fraction measurement down here. Choose your window size. So, what window do you want to slide across this image to visualize local area fraction with? We'll use the default, say generate. Now each pixel in the image has local area fraction calculated. Click any cell in this column and it's also visualized the same way. So we see now local hotspots and cold spots in particle area fraction, as well as a corresponding histogram of all area fractions observed in the image. Let's say we wanted to do some sort of interparticle spacing analysis. So let's actually remove edge feature step. So we've got the full matrix selected. Let's go back into local measure. This time we'll do local thickness. What this is going to do is run a skeleton along our matrix network, and at each point on the skeleton calculate the local thickness of the selection at each point on this red line, and then it's just going to smear out the color so that every pixel in red here is visualized with a local thickness value. So let's generate local thickness. Click anything in here. Now you see local separation distance between every bit of the matrix. High separation here, low separation down here. You can do line profiles across this if you wanted to. So you wanted to visualize this gradient here. Take your line, see a change. This can be very useful for doing layer thickness measurements. If you have layer thickness variations, you can plot a line profile down the center of your layer and see the thickness variations across it. So we're just scratching the surface on the quantification capabilities, but I wanted to show global, local, as well as feature-based ones. I'm going to shortly conclude here with the material science section so that we've got ample time for any questions and so that Paul has time to show you MIPAR's power on the life sciences section. So let me go ahead and demonstrate batch processing to you on another, actually let's just dive right into a very quick grain example here. Let me drag in this grain image. This is a tough one. You've got dark lines on some boundaries. You've got pure contrast boundaries with no etching has occurred at these boundaries. But we of course have the tools to handle that. So here's our recipe we've made for this grain detection. So we've got all these boundaries captured. I won't run through the logic here, but from the chapter titles, it's not too difficult to understand how we approach this problem. This recipe is available for you on the recipe store. Once your scale is calibrated, if you want to make the ASTM measurement per E112, that ASTM standard, come in here and use intercepts, since E112 uses linear intercepts to measure grain size. Take 1,000 random lines, just use the default settings here, and then in this table you'll see an ASTM grain size number of 6.2. Or you might choose to just use the mean intercept through all of the objects, 37 microns, as the grain size, however your company or university chooses to report this. But we do have the grain size measurement that conforms to the E112 standard. And there are a lot of other standards out there that really are conformed to based on the recipe in our case. So we've got recipes that conform to the volume fraction standard and the steel inclusion standard, And the, what are some of the other ones? We have the nodularity standard, A247, E45, inclusions in steel, porosity and thermal spray coatings, E20. All those standards really are recipes can be created and have been created to conform to those standards. And a number of those are available on our store. So I wanted to touch on that. Now, we've already shown how local thickness can be done. So I'm going to forego the core shell example that I had where it was measuring local layer thickness, since we demoed that capability in the matrix of those particles just a moment ago. So I'm going to conclude with a batch processing example. Let's drag in here a nickel-based superalloy example. This is actually a very interesting project. Tim was unable to join this webinar today, and he works at NASA at the moment, and they've done some fantastic work with a new imaging technique for measuring gamma prime in gamma matrix in nickel-based superalloys, measuring size and volume fraction. They've got a peer-reviewed paper now that is out for publication, and we are very excited to have collaborated with them and are confident that a combination of their new imaging technique with a MIPAR recipe, which they include in their paper, can very likely become the new standard for gamma prime measurements in nickel-based superalloys. So I'm very grateful for Tim's permission to share this with you today, and I wanted this to be our batch processing example. So here we've got two modes of particles. We've got secondary, these larger ones, and these very tiny ones called tertiaries. So a simple threshold doesn't even come close to working here, even though your mind might think it would. But we were able to put together a nice, efficient and robust recipe for accurately segmenting these particles. So the recipe is run. We've got the larger ones in green, the smaller ones in red. The volume fractions popped up here. The only thing I want to show you from this recipe is what we call optimization, because this is critical, at least in this case, to allowing such accurate quantification and allowing this recipe to likely contribute to this technique being the new standard. What optimization does is it lets MIPAR decide what it thinks is the best setting for a given step. A great example of that is an erosion step. So let's go right here to where we have the secondaries mostly selected after this algorithm was run about partly the way through. And if we take the erosion tool, you can see that if I hide this, I'm not exactly sure where this outline should be drawn. And you're never going to be. There's always a gradient that's going to be at play at the boundaries of particles. Do I stop here? Do I stop here? Do I stop here? Or do I go all the way back out here? I'm not entirely sure. I'm confident I don't want to grow it any further, but I'm not sure if I should shrink it. So in this case, what you can do is add one of those steps, add an erosion step, which we've done here, and then tell MIPAR to optimize it. So what this is going to do is say optimize. We are going to optimize it to memory image 1, simply because we've got the filtered version up here that we're going to use for the optimization. So this is our reference. This is what we're optimizing it to. Say optimize, choose your reference. We're going to consider the entire image, and we're going to use our metric of selection match. What this is going to do is just turn the knob on that erosion strength and automatically decide where to stop based on which erosion strength results in the best match between the selection and the reference image. So I'm going to let the strength vary from 0 to, say, 7 in steps of a half. So now it's shrinking it across that range, and it comes back and it says, aha, at a strength of 1 is when we have the best match between our segmentation and our reference. And now you have a mathematical, a defendable, and an objective reason for drawing the boundaries where you have. Not only that, but with this step being optimized, the next time you run this recipe, that optimization gets reperformed automatically. And if the next image needs an erosion strength of 2, that's what it's going to pick. And now you've got not only an objective recipe, but a dynamic one that's able to adapt to changes in imaging conditions if it needs to. So we did that for both the secondaries and the tertiary particles. We grew and shrunk them with this optimized dilation and erosion, and it came back and said they don't need any growth or shrinking. They're the best match exactly how they are already, which is still an important piece of information to know. It's still an objective selection then of the tertiaries. So that's our recipe. 2 modes, secondary and tertiary. Area fraction is in the measurement. So when you batch this, not only will you get all your segmentations, but you'll get a spreadsheet of measurements as well. But as you'll see, we like to review the batch before we measure. So I'll show that to you now. So you have your recipe loaded. You can launch the batch processor right from the launch bar. Or if you launch, let me save the recipe in its current state. Actually, let's just clear it out and load it back in again so you can see the workflow as you would typically conduct it. You drag in the recipe. You're comfortable with it on a given image. Maybe you've made some adjustments. Maybe you've resaved. If you launch the batch processor right from here, that recipe will be brought in for you automatically. So here's the recipe to batch. We've got 3 images here. We would just drag those in and say go. We're going to run this recipe now on all those images. It takes about 30 to 45 seconds. What you're then left with, once it's done, you hit View Results. That will automatically launch our post-processor or our processed image editor, which is really a quality assurance environment. You're able to now, with a slider, click through every image and see how the recipe performed on each of them. You can, of course, view this in all the same modes as in the image processor. If you want to look at the secondaries as an overlay, then switch to overlay for the secondaries. You can view this as an outline or as labels. You can export all images in whatever viewing mode you currently have. If you want to switch to the tertiaries, that's done up here in your layer selector. You're able to make manual edits in here if needed. If we wanted to erase any secondaries that shouldn't have been found, use your select tool, go to erase mode, just click on the ones you want to remove. It'll warn you that you have unsaved edits, so you'll want to hit save before moving on to the next image. We've got freehanding tools in here, of course, if needed. There are some magic wanding tools. We have a smaller tolerance on that. Not the greatest tool in this case, and not even really needed. Just wanted to demonstrate the capability to make manual edits in the case of a recipe needing adjustment. Sometimes you can go and modify the recipe just on a given image, save that image in binary view with the same name as shown here, and then that image will automatically update in this view. But this can be a very powerful quality assurance environment, as I mentioned, where you're able to actually observe how well your batch actually processed and make corrections if needed before performing your bulk measurements. So we have our batch processed and reviewed, and we're comfortable with the selection. Let's say we wanted to measure area fraction of both phases, of both particle types for each image. We would just check off area fraction and say generate on all layers, or you can choose a specific layer if you wish. And we now get for each image the area fraction of both types. We've got a pretty good match in this case, which is comforting for this particular experiment. You can copy this whole table and paste it. You can save it as an Excel file, or you can select individual cells and Control-C or Command-C on Mac to copy them. If you wanted to make feature measurements across all images, you can do that under Measure Features. You will have to select one layer or another in this case. So let's select secondaries. Let's say we wanted to measure their diameter and their eccentricity. Set the name of your spreadsheet. I'm just going to call this measurements. And then generate. So now we're going to get one big spreadsheet with all particles from all images measured. We also get a stats spreadsheet, and that message tells you where it's placed. And then because we checked make histogram, the big spreadsheet is automatically loaded into our histogram maker. So you've got now all features in all images all in one place. So here would be a histogram of all particles across all three images. All particle size. Here would be particle eccentricity. We've got some histogram unfolding techniques that can do some pretty cool things in estimating 3D particle size. I don't have time to go into that today, but it is explained in the user manual page for this tool. You, of course, get your statistics down here, mean, min, max, standard deviation. And then I also mentioned the stats sheet that was produced, so let me bring that up here quickly. Here we have the mean, min, max, standard deviation for each image for all the measurements that we checked off. And this can be incredibly useful. So that is batch processing, batch reviewing, and batch measuring. And again, there's plenty more to show and talk about, but with that, I wanted to conclude the material science section. We are about 1 hour now into the webinar. So I do want to move now into the Q&A section. Let me take a look at some of the questions that came in while I was demoing. If you can all give me just 1 minute, I'm going to go ask Paul a brief question, and I will be right back with you. Okay, I have returned. Thank you very much. So we were just reviewing the questions that came in during the material science section. We have a question from Elias regarding batch processing. So he asks that he mentions that during, at least in his cases, gradients and noise in the background can evolve during acquisition. In principle, one can tune the recipe separately for smaller batches, but is there a way to deal with this dynamically in a single recipe? It's a great question, Elias. I think all of us that work in material science, especially in image analysis, are aware that there's never a perfect image, that sometimes despite our best efforts, there are artifacts that are introduced, and those artifacts are not always consistent. So as you mentioned, they can come in the form of gradients, in the form of noise, or sometimes in the form of degraded phase contrast between phases. So you're absolutely right. There are many ways to go about that. Why don't I don't know that I have a very helpful example that can answer the question across all cases. My short answer is that it's really going to be a case-by-case thing. We have many different ways to deal with challenging artifacts in MIPAR. Sometimes they can be dealt with up front with pre-processing, with histogram equalization, with background flattening, with some of our more powerful noise reduction like non-local means. So you clear out the artifacts before you even launch into segmentation or feature finding so that they never have a chance to affect your other segmentation parameters. Other times we can choose to use segmentation tools like adaptive thresholding, which can work effectively in the presence of those artifacts. So those are kind of the two different higher level approaches to dealing with them. Either get rid of the artifacts up front or use approaches that are somewhat agnostic to them. Certainly, automated image analysis is facilitated by consistent and automated image acquisition. Good data in will lead to good data out. As you mentioned, in your case, the gradients and noise can evolve during acquisition. I've noted that myself in the past, working on SEMs where perhaps carbon is being deposited during scanning and is affecting your contrast, your global contrast in your sample. So I'm definitely sympathetic to some of these challenges. You are right that sometimes we can create separate recipes for chunks of 10 images and run each batch one after the other, and then bring all of the results, segmentation and reference, into the processed image editor so that you can review everything in one pass. So that's certainly an approach. You may also be able to set some of your recipe steps to be optimized such that they are flexible and intelligent and aware of some of the changes that are going on. But again, it's really going to depend on your particular microstructure, your particular artifacts, and the severity with which they change over the sample. Now, I'd like to demonstrate something briefly, so why don't I go to the crack and pour case where there was somewhat of a gradient there, and actually turn on pseudo coloring of the image, and sometimes that illuminates particular gradients a little bit more nicely. The jet map can be helpful here, so you can definitely see some sort of variation across the image. The simplest approach to background gradient correction is found under flatten background. Here you just choose your sigma value. Usually stopping at 1/3 to 1/2 is a good first attempt, and you see that will flatten out the gradient that is in place. But again, we could elect to just use, we saw the smart cluster work in the presence of this gradient before. An adaptive threshold, which I'm pretty sure you'll see Paul use in a bit, is also very adept at operating in the presence of gradients. We also have histogram equalization, where you choose how many tiles to split up the image into, and it goes and tries to equalize the histogram in each. In this case, we've used 7 different tiles. Crank this up to accommodate your particular microstructure. We also have a new set of texture filters that are fun to experiment with under feature finding. Just choose a small radius, and then you can flip through these, and a lot of times these can do some pretty impressive flattenings to your image. I mean, in this case, we basically dumped all the information except for the bright pores and the bright cracks. The gradient's gone, all of these background things are somewhat gone. So sometimes that can be an approach to just disregarding any of the other information that may have posed segmentation challenges. Some of these other filters, oftentimes it can just take you playing around in a sandbox like this to uncover a particular representation of your image that is going to work nicely. So my recommendation, as you know, Elias, our support is honestly in a league of its own. We get hundreds of submissions from folks every week sending us images to get custom recipes in return. As you know, we do web trainings for folks where we can, in a one-on-one session in a WebEx room, see exactly what challenge you're dealing with, make a recommendation as to how to adjust your recipe or even adjust it for you in the meeting. Certainly do feel free, if you're able to share, send over some of the images that you're struggling with, and our apps team can work to create or modify a custom recipe for you to help you out with some of those challenges. But thank you very much for joining, and thanks for the question, and I look forward to hearing more about it and trying to overcome those challenges. It doesn't look like we had any other questions come in during the demonstration session. Does anyone have anything that they wanted addressed? I'd say we have another 3 to 5 minutes for this Q&A session. Then that will leave Paul with about an hour and some change to work. Looks like we'll go over the webinar by about 30 minutes. We're here as long as you want us to be today. I'd say we could be here until 3 if needed, but let's aim to stop at 2:30. We want to make sure that we cover everything and get everyone's questions answered. So yes, what is the maximum image size? Is MIPAR limited by the computer resources or by MIPAR itself? Great question. That would be the computer resources. So the workstation I'm working on today has about 8 gigs of RAM, a quad-core processor, and a Quadro 600 GPU. And it is very capable of handling images with snappy response, I would say, up to 4K. We can load in images up to any size as long as you have the RAM to support it. Certainly as you load in images like 10K or more, you are going to see a degradation in performance unless you have a very powerful workstation to handle it. So no intrinsic image size limitations to MIPAR itself, all dependent on the computing power that you have. And as you may have seen in our latest release, we can now handle up to 50 channel images and using the bioformats plugin, which gets auto-downloaded the first time you try to open an image that needs it. We can handle over 140 different file formats from all kinds of different manufacturers. Statistics, thank you, Steve. So how are statistics calculated? Do they assume a normal distribution? We don't make any assumptions about the distributions themselves. let me load in here the recipe for this particular application so we can look at a histogram. If I were to make feature measurements of my pores, let's say we'll just go with their equivalent diameter. You see, we just have every feature and its diameter measured. And now you have a histogram of those features. So the mean, the min, the max, the standard deviation of these equivalent diameter measurements, those just come from the data itself. There hasn't been any curve fitting that's been done to this histogram. We do have curve fitting on the roadmap. Very shortly you will be able to curve fit a function of your choosing to, or have MIPAR decide the best one, to your histogram, since we realize that is an activity that many folks like to do, and it would be convenient for them to be able to do that directly in MIPAR. But at the moment I can't think of any distribution, any fitting that's done to distributions prior to statistics being calculated. The stats always just come from the raw measurement data. We had another question just now asking about edge detection. Can you extract XY data from the edges instead of just the calculated stats? Yes, we can. So as an example, let's go right in here to where we have the pores selected. I'm just going to clear out these steps in the recipe. We don't need the cracks for this example. If we add a perimeter pixels step, what this does is really select everything but the perimeter pixels. That's just a legacy functionality of that step that we didn't want to change, so that old recipes, we don't want old recipes to get negatively affected by this. So we would just invert this, and now we've selected the perimeter. Now what we can do is treat every pixel basically on the perimeter as its own feature. It won't truthfully be every single pixel. When you have a set of pixels like this, this will be counted as one feature, but it's still going to be a very fine step size in terms of coordinates around the perimeter. You can even visualize exactly what points would be exported. If I go and I say clean up, replace with centroid, now you have the centroid of every feature that was around the perimeter. So now what you can do is, let's say I do color by measure. Not that we really need to visualize this on a color scale, but it helps see the spreadsheet a little more easily. So if I measure the centroid now of every feature, and that's probably going to be quite a few, but it shouldn't take too long. So we've got 2870 perimeter points in this image, and you see each point now has their X and Y location exported. So to prove that, you know, if I colored every point by its X location, you see as we go left to right, these are higher on the X scale, since the origin is in this top left corner, and I believe, if I'm reading this properly, that, let's switch to Y just to make sure I'm interpreting this correctly. Yes, so 0, 0 is top left corner, and as you go to the right, your X increases, and as you go down, your Y increases. So this would give you now, this table is the XY coordinate of every perimeter pixel in the selection. We also then had from this the same participant in the image processing section, you mentioned roughness. What is your definition of roughness? Okay. Perhaps you might have joined a little bit later after we had reviewed roughness. If you go back to, it's in the manual in a couple of places. If we go to measure features and jump to that manual page, under the shape, there is a definition of what roughness is, ratio of the tightest fitting convex hull to the area of the feature. To demonstrate that, as I did, I think just before you had joined, let's erase these 3 steps here. I will go and take my pore selection, and I'm going to say replace with convex hull. This draws a convex hull around each feature. Now I'm going to take my actual pores and set them as the reference so that you can see the hull drawn on top of the features. And now you see this would be, actually I can measure this one directly. This feature has a roughness of 104. This one over here has a roughness of 108. And this one is probably a little bit higher still, 105. Right in the same ballpark, but you can see when we view the convex hull, this is going to be a rougher feature since it has the area of the hull that surrounds it is larger than the area of the feature. So the ratio of the area of the hull to the area of the feature is what defines roughness. Thank you for the question. And lastly, Jamie asked the smallest individual size you can detect with the software. That's a great question. We get that quite often, and really there is no size limitation. To us and to the software, pixels are pixels. And ironically, an image of atoms shot with a high-resolution atomic imaging microscope looks very similar to an image of trees shot by a satellite. So there's no intrinsic size limitation to what we can detect. It really comes down to how you've acquired the image. I mean, in that tree example, there's maybe 5 pixels per tree. For your particular purpose, that might be enough resolution on the trees if you're just interested in their location or possibly even their size. You probably can't get shape with 5 pixels per feature. And then you go to the atoms example, and with your high-resolution microscope, you may just have 5 pixels per atom in the image. It doesn't mean that that we can detect atoms better than trees. It's all just about the image, how you've acquired it, and whether your image has sufficient feature resolution in order for you to make measurements to the standard that you need to make them. So there really is no size limitation to features that we can detect. It's all about capturing objects based on their pixel characteristics. But thank you for the question. 3D images, I will just speak to that briefly. We unfortunately didn't have time to go into the 3D capabilities of MIPAR, but they are there. If you have the 3D extension in your software, what that will enable is this row of tools here. This is how we handle 3D images at the moment. 3D images need to be a series of 2D images, preferably in a folder. We will then build a recipe based on a representative image to detect your features. We will then batch apply that to all slices in your stack and assemble them into a reconstruction file that MIPAR handles. We then open up that 3D file in the 3D toolbox and can do additional segmentation, cleanup, what have you, directly in 3 dimensions in the 3D toolbox. Let me just open one 3D file so that you can see the capabilities. Here we've got a reconstruction of gamma prime, nickel-based superalloy. Again, this was a FIB data set, dual beam FIB, focused ion beam slicing with electron beam imaging. So a stack of this was collected. We ran it through the batch processor, which did the alignment, did the tilt correction, did the segmentation from our recipe, and now we can slide through from the different directions. You see we do have the full 3D data here. Turn on the segmentation, and you can see the fully selected particles that we have. Go to Labels, View, to see the individual particles colored separately. And then you can do some nice quick visualizations of things. So we can pick these 3 particles with our render tool and say go, and now we'll get 3-dimensional visualizations of those 3 objects here. And you can turn this into an animated movie. You can take a snapshot. You can measure 3-dimensional measurements or 2-dimensional measurements from this one slice. So here we have the volume of this feature. It's 3D diameter. And you can, of course, export these into spreadsheets the same as you can with with 2D measurements. Take 3D volume fraction measurements, so 3D volume fraction of particles here. Plenty of functionality in 3D space. I apologize that we didn't have time. We may do a dedicated 3D webinar at some point. We are also working on the ability for MIPAR to directly open 3D files. We should have that out in the next quarter, I would say. But right now, the way to get 3D data in is to have a series of 2D images that get assembled in the batch processor. And those can be any format over 140, like I mentioned before. So thank you for all your questions and attending this MSE portion. We're going to take a 5-minute break here and switch gears over to life sciences that Paul is going to lead. I'll field the questions, and again, in the same manner, if there are quick ones that come up, we'll try to handle them on the spot. Otherwise, we'll put them off to the QA section in the that will follow immediately after the life sciences section. So I'm going to, during the break, I'm going to open back up our agenda, and let me switch over to just sharing that application. And again, we'll take a 5-minute break right now, and we'll be back to talk about life science work.
Everyone, my name is Pavel Sul. I'm a senior application specialist here at MIPAR. My background is in biomedical engineering, and if you are submitting any sort of life sciences application for recipe creation, chances are it's going to go through me, and we'll be working together to put together some of these solutions. So today I wanted to get into colocalization, something that is growing more and more in life sciences. The techniques that I'm going to be demonstrating here can also be applied to SEM EDX images, where you have taken images of some particles and recorded data of their properties in different channels. But for this life sciences application, what we were going to do is kind of take a look at the problem that a customer had come to us with and see how we would have solved it inside of MIPAR. So as you can see, the image itself is a nuclear stain in the blue channel, a puncta stain in the red channel, and a nuclear marker stain in the green channel. What the customer was interested in is correlating the number of puncta, again in the red channel, to the intensity of the staining in the green channel. When it comes to problems like this, it is really important to kind of work with all the information that you're given. So, work with not only the nuclear staining, but the puncta and the grayscale information from the green channel to put together something that is robust and it can be applied to large data sets. So I'm going to go ahead and get started here to kind of put together a recipe of how we would approach this. So the first thing I'm going to do is I'm going to bring up my blue channel, which contains my nuclei, and apply a liner filter, which is really useful in fluorescence applications because it removes the granular noise of fluorescence while doing a good job keeping our boundaries relatively clean. From here, I'm going to apply a simple basic threshold simply because there's good contrast between the background and the features I'm interested in. So I'm interested in bright features. I'm just going to do an auto selection. The one thing that you may notice is that some of these have holes in them, and then we have some artifacts outside. So let me change my reference here to blue so we can see this clearly. I'm going to clean this up now by going through reject features and filling in the holes that I've done. Just measure this. It's about 99 pixels. I can overestimate, say anything less than 500. I'm going to want to remove. I'm going to reject features that are clearly artifacts because I know my nuclei are going to be in a range of several thousand pixels in area, while these smaller ones are only a couple hundred. So again, I'm going to overestimate, say anything less than 1,000, I'm going to reject. The very last thing I do when identifying these nuclei is actually making sure that I've contained only the nuclei that are of interest to me. Oh, actually, another thing I want to do is actually separate these two. This is the one thing I'm forgetting. We know that these two nuclei need to be separated. We could just do a separate feature steps here with a separation of 3. It's usually a good guess to get started with to make sure. And then if you see something not being separated, you can increase this. There's also other techniques that we use for approaching separate feature steps, but I'll show that later on in the webinar. So now that my nuclei are separated, what I want to do is, like I was saying, remove any features not entirely in the image because it's not really representative of my data. So I'm going to say clean up, remove edge features. And now what I'm going to do is I'm going to set this as a memory image. name this chapter nuclei. The next thing I want to do is actually go after the puncta. So we're going to go to measurements, channel operation, pick up the red channel, do the same thing where we apply a filtering step to remove some of the granular noise in fluorescence. I'm actually going to set this as a companion, and I'll show you why later on. But the next thing I want to do is actually run an adaptive threshold. And this is what I meant when I said that when we are working with these kind of problems, we want to work with all the information we're given. And in this case, we want to mask our selection of puncta to my nuclear selection, simply because I know that my puncta cannot be outside the nucleus, or the puncta I'm interested in will only be in the nucleus. With fluorescence, you can always find some noise outside of it, so this is usually a good technique to making sure you're not picking up something you're not interested in. So we're going to go ahead and pick bright, and by sliding our percentage bar, we can go through and see what looks okay and what's picking up most of my puncta without introducing too much noise into the segmentation. From experience, I know that a threshold of about 190 will give me a fairly good selection without having too much noise. I'm still going to clean this up by removing any pixels with an area of less than 2, which is really useful because, like I said, fluorescence data is fairly noisy. I'm not going to set this as a layer. Call it puncta. And the rest of this recipe, what I'm going to be doing is setting up the recipe for measurement generation. So I've now segmented the data I'm interested in. What I want to do now is to generate some measurements. So I'm going to set my puncta as a companion image. I'm going to call back my nuclei. I'm going to set this as a chapter actually. Say number measurement. So this is going to be my set this as a layer. Measurement. This way I know this is the recipe step that I want to be using to generate the number of puncta per nucleus measurement. The next thing I want to do is, we're also interested in a grayscale intensity of the green channel here. I'm going to set this as a companion. And again, call back my nucleus mask. We added this chapter. We're going to call this my green channel intensity. I'm going to go ahead and remove this as a chapter. I'm going to set this as my intensity measurement. So now that we have all the masks or layers we're interested in, we can generate some measurements. So to demonstrate what the customer was interested in, what we can do is go in here, say color by measure. We can generate the number of features in the companion, so based on companion, inside of each one of these nuclei. I can then select this, and these are colored by the measurement. I can just change this to 8. As you can see, it is somewhat normally distributed. So from this data, what I want you to note is that features number 7 and 6 have significantly less puncta per nucleus when compared to everything else. The next that was of interest was the grayscale intensity of the green channel. I'm going to do the same thing, color by measure, generate, look at the intensity mean and standard deviation, color this based on the measurement, and as we can see, all of our, oh actually to demonstrate this a little bit better, let me set this as a reference. That way my measurement makes a little bit more sense here. So we're measuring the grayscale based on the green channel, which is now our reference image. So as you can see, the 2 nuclei that had actually a lower number of puncta have now the brightest staining in this green channel. So this is, even though you don't have to do this for all of your images, and I mean visualizing what's going on, it is very helpful when you are validating your work. So it's great to see that you had a hypothesis and you're able to see that this is a trend in the data as you're working. So this is my selection for this recipe. The next thing that we're going to be interested in are actually the puncta themselves. So let me go ahead and change my reference image to the red channel and generate some measurements based on this. So some of our users would be interested in the puncta themselves, especially if you have multiple markers, so not just a general nuclear stain, but you have puncta in both the green and the red channel. So what's useful here is that we can generate not only area, but also the intensity mean of each one of these. In the next release, what we're going to have is an additional column of data that will return the parent feature identification. So in other words, it will tell you the feature ID number of the cell that contains that puncta. What this lets you do is correlate morphological changes of the nucleus or the cells to the properties of the puncta themselves. So let's see. To go back to kind of the material side of this, you would use a very similar approach to differentiating between particles that had returned signal in one channel versus another channel. To move on, the next thing I kind of wanted to demonstrate was the phase contrast image analysis, which is oftentimes very challenging because of the nature of the images themselves. So let me clear this out, load in one image. So this is a classic assay. Let me pull this up here. So the assay itself here's a citation. This describes the methods and the manual quantification of this assay, and the images were provided by a customer from University of Louisville. It's very much appreciated. So the challenge in this is that phase contrast oftentimes does not allow you to apply a simple threshold to pick up image data you're interested in and differentiate it from the data you're not. In this case, we're interested in the area of this wound or this empty area that's not occupied by the cells, and we're not interested in this area that is covered in cells. So this is a time series where we will have a, let me load in a couple of other images. So this is at 16 hours, 24 hours, and then 40 hours, there's no more wound. The challenge here is to be able to create a robust enough recipe to not only compensate for the variation in black balancing, and maybe there is some condensation on the lid of the well plate, but also make sure that, you know, when this wound is completely closed up, that I'm not detecting anything. So for this application, we built a recipe that, let me just drag and drop this in here, that is, you know, it's as simple as 6 steps long, but it's incredibly robust, and it's able to pick this up consistently, and I can demonstrate that now. So the first thing we do is we do a adjust contrast to kind of adjust the levels of this to make sure it is consistent enough for the bright texture algorithm to run. And what this does is, this is incredibly powerful because it brightens regions that have bright texture in it, and it darkens the regions that do not. This is useful to us because we know that the wound itself will not have a lot of texture in it, but the cells will. So from here, we apply a simple basic threshold that is adjusted, looking for dark features. We then pick up the largest feature, apply a cleaning up step to remove anything in the edges that would have been picked up. This is really useful because oftentimes what happens is when cells around the edges, they get incredibly dense. It's kind of hard to differentiate between a texture in incredibly dense cells and in the wound itself. So removing something around it is actually really helpful. The last thing we do is we just fill in these holes to give us the wound itself. So this is entirely, let me just save this really quick. Let's and then demonstrate this. So this is entirely batchable. This allows us to apply a single recipe to all of the images, even the ones that do not have a wound at all. Another set is much different in intensity, and this is still being it's still being selected properly. So a recipe that is this robust is very helpful in having a high throughput type of laboratory where you know that as long as you capture your images consistently, you can apply the same recipe to hundreds if not thousands of these and get data that you can rely on. I would still recommend to go back through and do some quality assurance in the batch process in our process image editor, but I would, this is a recipe that is fairly impressive. The next thing that I wanted to discuss is again in phase contrast, and it's something as simple as cell counting. So this is a higher, oops, did load the wrong recipe. So this is a higher magnification image, which just has some cells in it in different morphologies. You have some rounded ones, you have some elongated ones, but as you all may know, it is incredibly difficult to quantify something like this without an additional stain, but we can do this in MIPAR fairly easily. This is a fairly long recipe, and what I want to demonstrate with this recipe is a recursive separation. So I'm going to go through this fairly quickly to kind of demonstrate exactly what I wanted to show here. So again, this dark texture filter is very useful in identifying these cells in phase contrast. I'm able to pick up the background. It just changes to overlay. I'm going to set this as a companion image. I'll call back my original image and actually remove the background, leaving only the cells. This is very powerful because what's happening is the cells that it's removing most of the separation between the cells while keeping the information of the cells themselves. We're able to identify this, do some cleaning up, and then get into what we call a recursive separation. And what we mean by this is that we cannot apply the same separation strength to every single one of these cells at this point. This is because if a cell has a certain geometry and you apply a stronger separation that would have been used for a larger clump, that chances are that that cell will be separated, causing an artifact in your measurement. So the first thing we do is we simply remove any cells that we're pretty confident are actually already well separated. We're then going to fill in some holes, and then we apply our first separation. And fill in the holes again, and then reject any of the smaller artifacts that we would have noticed. We're going to set this as a memory image, reject again features that we believe are properly separated, leaving only clumps. We're going to separate using a higher threshold, so in this case it is a 1. In the first separation that we applied was actually a 3. I'm going to reject any noise that we've created, set that as a companion, and then now we recombine all of our data again. So what we're able to do is call back our pre-separated image, reject the clumps from before, and reunite the separated layer. And then the very last thing we do is recombine the cells that we removed in the very beginning. I'm going to go through this very quickly. And as we can see, I apply a very last separation. To kind of help separate these smaller clumps that would not have been separated before. So if we go in here, go into our labels view, we see this is done fairly well. And, you know, I'm not going to pretend like it's perfect because it is not. But if you were to sit down here and try to quantify this manually, this automatic quantification is well within the margin of error when compared to manual quantification of high throughput imaging. So I went through this actually fairly quickly, and let's see if we have any questions from anyone. So Brian has a question about deconvolution. So deconvolution is a process that is used, is a technique that's used to separate, oftentimes histological staining of tissues to remove, to separate the image based on the stain itself versus separating image based on the red, blue, and green channels. A classic example is H&E staining, where what you want to do is separate your hematoxylin from your eosin. We're able to do this. MIPAR is actually very robust when it comes to channel operations and work in that field. I don't know if I have a good example. I think we have something on our recipe store. One moment. So this is an H&E staining. I forget what the tissue is. But oftentimes what you'd be interested in is something like generating a cell density count of this tissue, or kind of morphological changes in this. An approach that we would take is create a deconvolution is basically a set of channel operations between the three channels that are given to us, because the image is given to us in red, blue, and green, to give us the isolated eosin stain and to give us an isolated hematoxylin stain in grayscale. I don't remember if this recipe here is I might have used deconvolution here, but I do not remember. So right now, actually I did. So right now, as you can see, this channel operation is fairly long. It's fairly messy. The way we approach deconvolution is you can submit the image to us. We can create the deconvolution matrix for these channel operations and give this back to you. We are working on a built-in deconvolution tool that would allow you to do your own deconvolutions internally within MIPAR to generate these channel operations that result in the stain of your interest. So this is fairly challenging if you approach this from a simple image approach, but with deconvolution we're able to almost erase all the hematoxylin data and keep only the nuclei. Okay. So let's see if there are any more questions. Okay. We actually have a little bit more time. We went through this a little bit faster than I thought we would. So if anybody has any questions or would like to see something demonstrated, go ahead and submit the question to John or myself.
Yeah, thanks, Paul. I just wanted to hop back on quickly and speak a little bit more to the deconvolution question, which is a great one. Like Paul mentioned, how we handle this right now is we actually have a recipe built for ourselves that is all set up for us with the manual edit tool to basically go in and just trace a little bit inside of, say, stain 1 and a little bit inside of stain 2. And then what the recipe will do is it will spit out average intensity measurements in each of the red, green, and blue channels for the tracings that you just made in both stains. So you get average RG and B for stain 1, average RG and B for stain 2 based on what you've traced. Then we take those intensities, we put them into some code that is actually pretty simple to create and is just based off of a paper that's out there that we'd be happy to share, and I think is even shared through our user manual in the channel operations section. Potentially, I'll check on that. But we take those intensities from the recipe, we put them into the code, and that spits out then this channel operation that you see listed here, which, as Paul just showed, is quite powerful. So, like you mentioned, what we can do is, for now, you could even submit to us the raw image, the raw RGB image, and even masks of the tracings that tell us exactly what features you would like your deconvolution to be based on. And we can then turn around a recipe in a few minutes for you that has those channel operations in there, and now you're good to go. And if you only use those 2 stains, you'll probably never need another deconvolution ever again. But like he also mentioned, we're in the process of working on a graphical tool that'll let you do the tracings and run, calculate the deconvolution matrix for yourself, all inside of MIPAR, so that you can come up with the channel operations yourself. To this date, most folks have been very happy to just receive recipes with the channel ops hard-coded in that work for their particular deconvolution case. And we're very, we never set out to even put deconvolution into MIPAR. I didn't know what it was until 2 months ago, and it turns out the channel operation tool that we have in there is perfectly set up to handle deconvolution of nearly any case. So it's very exciting when you find, when you build a tool that's flexible enough to add more functionality to itself without any coding than you ever really envisioned the tool to have. So that was pretty exciting when we came across the deconvolution capabilities. But we're working on that tool, like I mentioned, and that should be out in the next 2 to 3 releases. So thanks for those questions. It looks like we had a couple more come in while I was speaking, so I'll mute my mic and turn it back over to Paul to let him answer the few that just came in.
Thank you, John. Still waiting for my sheet here to update.
Oh, sorry about that. I realize now that those questions came in to me privately and that you aren't seeing those in the chat. So I'll read them off here as I put them in the sheet for you. We've got a question from Jan asking, can we do auto threshold? And certainly the answer is yes, in more ways than one.
Yeah, let me demonstrate that using our colocalization example. So oftentimes what happens is your images are not perfectly black balanced, and what we've recently added was a pre-processing step that allows you to adjust contrast. If you click auto, it brightens everything. Auto low will auto black balance your image, and auto high will auto bright balance your image. So this is fairly useful, especially for in fluorescence. If you want to black balance your images, you cannot, always can capture perfect images. So, and this is very helpful, especially if you have a little bit of variation from image to image, and you're trying to run a batch process, and there might be some variation in the balancing here in the background. So the answer is yes. Have you created, the next question is, have you created recipes for comet assays calculating DNA damage? We have not created any recipes for that, but we would love to see that. Yeah, you're welcome to send over any sample images you may have, or as well as a published paper on this essay, and I would love to be able to recreate it inside of MIPAR. Chances are is, if you can somewhat visualize this with your eyes, we can get pretty close to quantifying this automatically, or at least semi-automatically. Are there any more questions, John, did you see?
I did not see any more questions come in on the life sciences section. We got a question on 3D reconstruction for porosity analysis and whether that can be demonstrated. Let me give that some brief thought while we actually just have a couple of more come in on the life sciences side. And just to add just a couple more points to the auto threshold question, like Paul mentioned, oftentimes what he was speaking to was how we can use our contrast tool to auto set the contrast, which can then assist in running a basic threshold with auto mode. Usually if you put some kind of normalization step ahead of auto threshold, then auto threshold works even better, and that's exactly what auto contrast low high or both is as a normalization step. Like I demonstrated during the material science section on the simple particle case, we had a couple of ways to approach that problem. We either could have just used an auto threshold bright to automatically set a threshold value to choose bright features. We elected to go with a smart cluster, which is really a auto multi-level threshold. So with a smart cluster of 3, you will automatically divide the image into 3 different classes, which can often be more robust than just choosing auto 2 classes. The trouble with auto 2 classes is that sometimes your other gradients in the image can affect what the software decides. Gradients can affect how the software decides that auto threshold limit, and if your features are decidedly darker or brighter than the background, then using a smart cluster of 3 or 4 and then just choosing the brightest or darkest class out of those 3 or 4 can often be a more robust way to auto threshold something. We then also have the adaptive threshold that is far more robust and flexible than a basic threshold. The adaptive threshold, as Paul demonstrated, selects objects based on their being relatively brighter or darker to their immediate surroundings, not just on an overall brightness scale. And then the fact that you can optimize an adaptive threshold step to have MIPAR decide where to drag the percentage slider to puts an auto mode basically on the adaptive threshold. So again, optimizing the adaptive threshold percentage value is an auto form of an adaptive threshold. And do feel free to visit the documentation page on optimization. That can be applied to a number of steps in the recipe. They're all listed in the documentation page. Like I demonstrated, we often use optimization on erosion and dilation steps to basically have the software using erosion and dilation snap the selection boundaries to where it thinks they best fit the feature and take a lot of the subjectivity and a lot of the penalty away from, over or under selecting your features by a couple of pixels, which for area fraction measurements can also sometimes, throw them off by 5 or 10%. So definitely a lot of auto capabilities. And I also wanted to throw this out there. We're so excited, and I would say the next 2 to 3 months, if we hit our roadmap, we are working on some AI tools that will allow you to trace some features of interest and have the software auto-select the majority of them for you with a single recipe step, where you can then still add additional recipe steps for further cleanup, like lower and upper size limits and separations and other things. But we're excited for the new frontier that adding some of those user-trained AI tools will bring to MIPAR, and we expect those out again in 2 to 3 months. Just wanted to add that in there since we were talking about auto capabilities. I don't think we have time to go into a full demonstration of another 3D reconstruction. I did show what the finished product of a 3D reconstruction looked like for bright gamma prime particles, and certainly pores are even easier. I mean, you could just imagine inverting that 3D data set, and now your particles are black and they're just like pores, and we would come up with a recipe for the pore detection. We would batch that on all of the slices. In the same batch process, assemble the data set into a 3D file, open that 3D file in the 3D toolbox, slide through it, spin it around, maybe do some artifact removal directly in 3D. We'd be happy, Sheena, to set up a one-on-one session with you if you had a specific data set that you'd like us to demonstrate this on. I mean, usually your particular data set of interest is the best use of your time. So if we could demonstrate something to you in a session on your porosity data set, we'd be very happy to do that. You're welcome to book a training, as anyone is, at mipar.us/training. I'm just typing that into the field so you can see it. Also, you can just go to our website, and from the support section, there's a training tab, and that's how you can schedule an online training with us. Absolutely, you're very welcome. So I'll let Paul then finish up just with the 2 more questions that came in, and then let's move on to just our closing comments section. Looks like we had another question from Jan here. Let me paste that into the Q&A section. She asked if we can average several images together or calculate maximal intensity images. So let me let Paul speak to that.
So I'm guessing you're referring to kind of collecting, if you have a Z-stack from confocal images and you have data at different Z's that you want to compress together to minimize the noise and maximize the signal you're interested in. At this time, we don't do it directly in MIPAR. There are some workarounds that we can do to achieve this. Yeah, oftentimes it's much more efficient to do this in on your acquisition software. So the software that you use to capture these images oftentimes allows you to export the images in a certain fashion where the maximum projection is an option there.
Great. Thank you everyone for the questions, and thank you, Paul, for fielding them so brilliantly, if I may. If there are no more outstanding questions out there, looks like we've We've managed not to go too far over our time. We're at 1:20 here Eastern. Like I mentioned when we opened, we've had some folks join our webinar who are early adopters of MIPAR and have been fantastic users from the very beginning, and they've volunteered to speak to some of the use cases that they found for it to see if their experiences could be helpful to others in the webinar. So let me just see if Brian from Iowa State is available to call in as he requested, and see if he can share some of his experience with you. While we're waiting on him, yes, and Chenling, do feel absolutely free to contact us with any questions directly, either through our support email, our live chat, or our phone line. While we're seeing if Brian is available there in Iowa, I wanted to, again, first of all, thank everyone for your attendance. We've let, it's our intent going forward to try to host at least one of these webinars per month. Many have spoken highly of their effectiveness and efficiency in covering a wide range of topics and really showcasing a lot of the capabilities of MIPAR. So thanks everyone for joining. We welcome any and all feedback on this webinar. We always strive not only to make the product better, but the support experience better. So if you have any recommendations for ways to adjust the structure of the webinar, or you have specific topics you'd like covered in the next one, definitely feel free to reach out through live chat, support, or phone. For now, we plan on having the structure be somewhat similar to today, maybe with a little more emphasis on 3D if there's an interest to that. But we'll definitely keep you updated via email as to when the next webinar is going to be, so that you're able to register. As I mentioned at the beginning, we have been recording this from the very beginning, and we will share that recording link with everyone who has signed up once the webinar is over. In that follow-up email, you will also get links to download all of the images and recipes featured today, so long as we can get permission from their owners for each of them. But certainly all of the ones that are from the store, which is the majority of what we've shown today, will be available to you in one package shortly after the webinar. I also wanted to mention, if you're not already aware, that you may, if you have not already, download a free 30-day trial of MIPAR from our website at mipar.us/trial. And as we've mentioned a couple of times, mipar.us/training is where you can sign up for a one-on-one session with myself, Paul, or another one of our app specialists to get, again, one-on-one training, demo, and assistance with your particular problem. And then lastly, mipar.us/tryimage is where you can visit to submit any of your images to us for custom recipe creation, or if you're already working on a recipe, shoot over the recipe and the image, and our team can help tailor it to your specific needs. And then, of course, mipar.us/recipe store is our ever-growing repository of pre-built recipes that are always freely available for you to download and get a jump start on both learning the software as well as tackling your specific application. So it looks like we do have Brian available, and he's willing to speak a bit to how he's been able to make use of MIPAR there at Iowa State University. So thank you so much for calling in, Brian, and attending the webinar and being willing to share. The floor is yours.
Yeah, of course. I mean, there's not much more I can add here. Everything was pretty well covered, but so I guess I used it for quantification of titanium microstructure, both SEM images and optical images. I'm looking for both segmenting out different phases, which are pretty clearly just a two-phase type microstructure, as well as quantifying different types of morphologies. And it's difficult for me to say because I am pretty new to image processing, and MIPAR is really all that I've used. But I have dabbled with like ImageJ a little bit, but really what makes MIPAR stand out not only is everything, in a nice package where everything is laid out nicely and you could see what clearly what each step is doing, but the recipe framework and the batch processing means that once I get a recipe figured out and I can edit it any steps back instead of having to go all the way from the beginning, is really what makes MIPAR useful for our purposes. So.
Sure. Thank you. It, as you know, means the world to us to hear that sort of feedback. I mean, we developed MIPAR as users ourselves, so we definitely created it for the very research that we were doing and to help overcome the limitations we saw in other tools that were out there. So it's certainly gratifying to hear other users echo some of the same sentiment, and we really appreciate all of the feedback that especially you and your group at Iowa State have given, because it's helped shape where the tool is today. I mean, we're very eager to receive feedback from anyone who's willing to offer it, and a number of our users have told us that a big reason why they've gone with MIPAR is our team's willingness to implement feature requests and modifications that they bring up. So we very much value our users' willingness to share and offer their feedback and suggestions. So is there anything else that you wanted to add, or did you have any other questions from anything that we've covered today? You guys still getting along with it well at ISU?
Yeah, no, it's been great. It's been a great help for really taking microstructures and being able to put quantifiable data onto them. And especially now we're able to batch process these images, rather than you're not limited by time, where once you have a recipe figured out, you just run it over, your 100, 200 different images and get your quantifiable results.
Sure. It's definitely, I mean, as a former grad student postdoc research staff member at Ohio State University, I definitely know how overworked we all are, and having a computer churn out some results while you're getting some much needed rest is valuable in and of itself. And you guys are also doing some really cool things with the data that MIPAR spits out. MIPAR really today at least is a data retrieval tool from images. Once you have, and you're doing some really great things correlating some of that microstructural information back to mechanical properties of the material to figure out what some of those relationships are. And it's great to see it put to such important use, because the whole ICME effort, being able to, in a computer, predict how your material is going to behave given how it looks under the microscope is a great new frontier. And you guys are even doing some stuff with genetic algorithms as well, I believe, to bring in some of
it's sort of a genetic algorithm neural network coupling where they're sort of checking against each other to verify that our models are accurate.
Yeah, that's really exciting to us to hear. I mean, down the road, we see MIPAR potentially being able to bring in some of those data analytics tools and being able to generate these neural networks itself from the microstructural data that it pulls out. And if we get to that point, your input on how you do that today and ways that could be improved would be really awesome to hear. But it's great to see you making such good use of the data today.
Yep.
So thanks again so much for joining and being willing to share.
Yeah, of course.
Well, you take care in Iowa there. I hope the weather is a little better than it looks to be in Columbus these days, in Ohio, but I don't know.
It's cold and snowy.
Cold, snowy, and fluctuating, so it could be 70
Yep.
degrees tomorrow, right? Fahrenheit.
Mm-hmm.
Okay, well, you know, we don't have anything else from our side. Again, you'll get links to download the recording and the recipes and the images that we're able to share. We'll be hosting these more frequently, at least once a month, as best as we can. We just had our 150 release come out a couple of weeks ago, and 151 is not too far off. We've got some additional enhancements to make and a couple of cool, really new features that we want to get in your hands. Those of you that have updated know that once we put a release out, if you have internet connectivity, you just launch MIPAR and it auto-updates itself. If you don't have internet connection or you've got firewall issues, you can visit our update page and manually apply the update that way. But you'll be notified once the 151 release comes out and reminded of how to get it and how to view the release notes. So don't be shy with any suggestions or feature requests, especially once we're in active development on the next release, where we're very adept at taking your suggestions and quickly turning them into real features and tools. So if there's nothing else for today, we'll go ahead and close this one out, and you'll receive a follow-up email from us shortly with all of the post-webinar goodies that I mentioned. Thank you so much to everyone for attending, and we will see you in the next one.